Hello, anybody here? So let's check our session. Looks good so far. Okay. So hello, whoever is seeing this. I'm streaming this with Restream.io. That means that we will stream it on multiple devices, multiple platforms at the same time. So that means on YouTube we are on the channel SQL TV, my regular channel, and on Twitch we are on my gaming channel. I will just retweet this into the network. Unfortunately I cannot monitor the chat right now, at least not so easily. Maybe I can overcome this next time. So we are connected with both, and let's just stream is online. Stream is online. Topic is index basics today. Okay. Okay, I have to relay this message on Facebook to my channel as well, and then we're set. So, okay, that didn't work so far. Let's just have a look at Twitter if it succeeded. Twitter SQL. And let's check my messages. Okay. Okay, for some reason this did not work, so I will just put it manually here. 1 second. This stream is online, index basics, and we put the Twitch and the YouTube link there. So this is Twitch. This is YouTube. Next time I will sort it out before, hopefully. Switch accounts, here it is, and here we have the YouTube channel. And we are live here, so my channel should be it. Exactly, here it is. Good. Okay, so this session is about the basics of indexes. That means we will just cover some very basics of how to understand why we're actually using indexes, and or how we in general store data in SQL Server. So short notice about me. If you did not see any of my videos yet, please have a look at the YouTube channel that is linked also. Somewhere, if you're looking this through YouTube, it's easy. If you're looking this through Twitch, just have a look at SQL TV, that is SQL TV, and you will find a few videos. I think I made 20-30 videos about some technical stuff for YouTube. I myself studied computer science in bachelor's and master's at university, majoring in databases and efficient algorithms. I did several projects before and during study time, which is completely normal for a student, I guess. And for instance, a browser game and a crypto database. I started with working with SQL Server in 2014, and in 2015 I became MCSA in SQL Server 2012, and in 2016 I became MCSE in data management and analysis. So, just did you know who is talking to you? So let's come straight to the first question. How is data actually stored in SQL Server? We have to approach this in two different kind of levels. So the first level always is the logical level. So on a logical basis we have rows, we have tables, and we have something in between, which I come to right now. And on a, let's say, physical level, we only have, of course, files, data files, and nothing more, basically. What is on your Windows drive or on your Linux drive is always files, and this is the physical level. So first of all, I want to talk about row-based storage. So normally, if you don't specify something special, you will create a table that is row-based. What does it mean? So have a look at this table state. That is create table ID int, first name varchar, last name varchar, means I store here some names. So ID 1 is my name, ID 2 a colleague of mine, 3 colleague of mine, 4 colleague of mine, and so on and so forth. The point is we store it one after another. So we begin with ID, first name, last name. Then comes another ID, first name, last name, and so on and so forth. And since you cannot see my cursor here, let me just set it up that you can actually wait, how can I do this? It's actually important that you can see my cursor. Capture cursor is enabled. I know you can see it. Okay, so we store every row one after another. Of course, it's not the real delimiter is not semicolon, but you know what I mean. We store it one after another. So multiple rows are now not saved in the whole table, but they are saved on something called data page. A data page is also a logical construct which basically consists always of 8 kilobytes, and it can save up to 8 kilobytes in row data. That means if the 8 kilobyte exceeded, you will get another data page where you put the row on. That's also a logical construct. Then another logical construct, which is not so important right now, but it is present, so it is good to know about it, is an extend. An extend is a set of 8 data pages that are, of course, 64 kilobytes in size, and SQL Server just keeps track internally not of pages but of extends. That's why I mentioned it here. So now coming to table, what is actually a table now? So a table can be two. It can either be an unordered cluster of data pages. So you have many data pages where your row data is at, and basically you have one big index file or index page that shows you and that tells you what other data pages are belonging to your table. This is called a heap table. And you can have the other part, that is the ordered structure. It is a Btree structure, and this is called the clustered index table. And now we come to the question what is actually a Btree? I call it a Btree. Those of you who studied computer science or heard something about computer science stuff before may know what a Btree is. And those of you who don't, I will do a quick recap. In order to maintain order or structure on the data, we use a Btree, or SQL Server does use a Btree. So a tree in computer science is a hierarchic abstract data type. There's a root consisting of nodes that are linked to each other. A root node is the entry point to the data structure, if you want so, and there are leaf nodes, like in a tree has root and leaf, and those are at the bottom, that are the last level of the tree. The Btree is always ordered in some certain way, and I pull Wikipedia up here because actually I have a good example for this. So let me just show you this picture here. So here you see a Btree. You see the big blue node with 7 and 16 in it is the root node, because it's the first node. No arcs are going into this one, only out. And here we have no intermediate nodes, but we have 3 leaf nodes. You see the leaf nodes have no outgoing arcs. An intermediate node would have both incoming and outgoing arcs. Here you can see the root node contains 7 and 16, and you see on the leaf level there is an order 1, 2, 5, 6, 9, 12, 18, 21. It's ordered by this integer value here. This is very important because this is how we can actually utilize the Btree. So now consider you have n values and you have a list of n elements, and you want to access a random element which you don't know yet. Then the access time you have for this one element is O of n, which means basically that you have the maximum steps you will have to do is in the complexity class of n, that is the linear complexity class, which sounds a little bit complicated, but just means in the worst case you have to scan all of the n elements. It's because if you're looking for the last one, then you have to go through all elements until you see it. Or if you will, so you're coming from 2 sides, then there's the half of it, but it's still the same complexity class linear time. A Btree, however, if you want to have a certain element of the Btree and you are accessing it through the key, through the Btree key, in this example it's only the integer value is existent, then you don't have to scan all of this leaf nodes. You just have to scan at maximum the logarithm of n elements. What does it actually mean, logarithm of n? Okay, you heard it in school. What does it actually mean? You probably forgot, but let me show you an example. So in this example, look at the left hand side first. We see an n for 10 million, 20 million, 30 million, going to 100 million, going to 200 million. You see O of n is of course exactly the same number. If I ever have 100 million entries and I'm looking for the 100 millionth entry, of course I have to go through 100 million entries. But if I'm looking at the logarithmical complexity class, I have only 7 nodes to scan, not 100 million but 7. And you see also it grows very small, very slow. If you look at 200 millions, you have only 7.3, which will be of course ceding to 8 accesses. So instead of scanning 200 million nodes, that is in the end 200 million IOs somehow, I can only also do it with 8 IOs. And of course you know that IOs are the very limiting factor in databases, or in every computer system. IOs from disk, I mean, then of course 8 is much better than 200 million, isn't it? So you can also see it here in the graph. The orange is a linear, the linear curve for O of n, and for O of logarithm of n you see this gray thing. And be careful of course for the gray thing, for the gray curve the second y-axis holds and not the left, the first one. So there is a big need that we want to have Btrees in order to get those very small IO steps in contrast to the full table scan values that we have here on the left hand side. This is where the clustered index basically comes into play. Let me just check here. Okay, so what is actually a clustered index? A clustered index is nothing but a Btree. So you can obviously have only one per table, since the table itself basically is exactly the clustered index. It's basically the same terminology. If you have a clustered index table, the table is the clustered index, and therefore is the Btree. So you have your whole table structured as a Btree. That means that the leaf level is ordered on the column that the index is created on. if you create a table ID first name last name like I had it in my example, and you order it on ID, you will have an index that is consisting on ID. For these purposes, let me just have a quick look at this little piece of software which is not yet done, which I created. So if you create a table on ID and the primary key, so the cluster index you set on ID, and you have some first name, for instance, give it a name, first name. For the sake of easiness, I want to make a very wide field here so we can actually see a few nodes creating. Or let it be even 5,000. And then let's create an insert statement, or let's create some artificial insert statements. And then you can see here, like first we have my name, then we have like a second name, then we have like Joe, then we have like Zuma, and then we have let's say Picard. Okay, so if we now plot this, basically we have here the root node, the 0, and yeah, actually we start with 0. So then comes the first, the second, the third, the fourth, and so on. You see, this is the ordered. Like, okay, let's just copy this, because actually let's make it possible to only have one entry on a page. So we put this to 7,000 bytes and do the same step. Then each name should be, well, that didn't work. I think we have to convince him somehow. Let me check this. Generate inserts, override, simulate. Yeah, now we see each entry is a new node. Of course, in real life this is not the case. In real life you have multiple entries on your data page. But just to tell you, so this, when it's all laid down, you see here you have a Btree with one node pointing you into the direction, and you have those entries in the order of the IDs. If we go now and say, okay, the primary key isn't anymore our ID, but in fact it is now our first name, and we do the same stuff. It's something he didn't like ID int first name primary key. Okay, but it should do something else now. Primary key, no, I didn't have any typo in here. Does it work with those values? Yeah. Ah, of course it doesn't work, because this is now integer. I have to put here for some reason he expects here also no integer values. Okay, as I told you, this is a small piece of software I created basically with okay, so somehow it doesn't seem to work with this right now. I don't know exactly why it works with the okay, but what you can see already here is that the order is then of course vice versa. That's what I just wanted to tell you. So then in this example, what I would have laid out, there would be first this name, then would be this name, then this name, then this name, and so on and so forth. So it would be not be in the order you have the IDs, but in the order you have the names on. So the intermediate nodes are not very special. We have an example of a Btree in a minute, where we can actually see intermediate nodes, and the leaf nodes contain all the data in a clustered index. Since the clustered index is your table, on the leaf level you will have all your data, and in the intermediate, in the root page, you will only have your key column that you put the index on, and some pointers to the next level of the tree where you can find those particular data. And of course on the leaf level you have a doubly linked list. So all the leaf levels are linked together in order to perform an easy table scan if you have to do this. So now coming to a non-clustered index, it's actually the exact same thing. So non-clustered index is also in Btree. It is also containing root nodes, intermediate nodes that have exactly the same structure. Like they have the key column on which you put the index on, and they have pointers to the next level, only that now in the leaf level you don't have all your data, because of course data is in your clustered index. On a non-clustered index you will find the key to the clustered index for that row. For instance, assume you have a table ID, first name, last name, and the clustered index is on ID, and you want to query fast all the guys that are called Miller with last name. So when you just type select star from table where last name equals Miller, it will scan the clustered index on the leaf level for each entry. So you have basically the slow version of it. If you want to do a faster version, you put a non-clustered index on the last name column. That means you can look up through the index with the last name and look for all the IDs that contain the last name Miller. And with those IDs, you go to the clustered index and you find it. This technique is called key lookup. And as you have here two examples, let's just have a look at the left one first. So an index seek is basically if we use the structure from the root node on, and an index scan would be if you just start from left to right on the leaf level, which will be the slow variant, where we version where we basically scan all n elements, but the seek will scan less elements. As you can see here, if we know our name, for instance, starts with P, like Picard, we would go here and ask, okay, where is the P names? And the root node would tell me, okay, go right. Then this intermediate node, I ask also, where are the P names? We know this node covers L to Z, so P is in here. And there is a pointer in here that tells me, okay, if you're looking for P, you have to go the middle one. And in the middle one, I have finally found my name. And I did this by doing 1, 2, 3 steps instead of 1, 2, 3, 4, 5 steps. Okay, this is a small scale, but in the big scale you saw already that the number of lookups does not really go very high. You know, you have at least in SQL Server an index height of 4 or maximum 5. No matter how many data you push into it. You can have millions and billions of rows, you have only a maximum of probably 5 in height. So you have 5 IOs. So you find your designated data set. This is the general approach for index seeks. On the right hand side you see what I actually meant with non-clustered indexes and key lookups. So we have here two indexes. The first one is the non-clustered index, and the second one is the clustered index. You always have the clustered index, and in this case we have a non-clustered index. So let's assume we have our example with the last name. We go in here and we search for all guys called Picard. Okay, we go here down this structure with very efficient, only 4 or 5 IOs. We find in this leaf level of the non-clustered index, we find, okay, Picard, there are 5 names with Picard. They have ID 5, 50, 100 and something else. Okay, let's say we have only 3. They have 5, 50 and 100. Okay, IDs. That doesn't help much because we still want to name the we want to have the first names. The first names are not stored in the non-clustered index. In the non-clustered index we have only IDs and last names. But with the information that we have Picards in ID 5, 50 and 100, we go to the clustered index, and this is built up on the ID. So now we go to the root node and ask, okay, where can I find 50? And it traverses you here. Okay, here's the 50. And there we find Joe Picard. Then we ask, okay, where's the 100? The 100 is down in the middle here, and we find here the 100. Okay, this is Jimbo Picard. And then we ask, okay, where's ID 100 or 500 or whatever, the last one. And we go here and we find this then in this leaf node. And here is the last one. It's called Robert Picard or whatever. So This is the whole idea. So to put the clustered index on an artificial, very narrow column to make it very efficient. We come to this maybe in another session, or you can also have a look at my videos. I explain actually in some of the videos to clustered index why we should have a narrow, artificial, ever increasing key. Like an identity column is perfect for this. But it won't help us, an identity column, to really utilize the clustered index operations, right? So we build a non-clustered index in order to find those IDs that we build, and then, for instance, by building it in first name, and then we can easily access all our data. Of course, the non-clustered index will be almost always be very much smaller than the clustered index, hence the benefit. So this is basically these are the very basics of clustered and non-clustered index. If you want to know more, you can have a look at my videos on YouTube. Again, the channel is named SQL TV, and you can have a look there on detailed videos about clustered and non-clustered indexes. But we will go a little bit further and talking about, actually, let me have a look here at the definition of a key, because many people mix up primary keys and clustered index. It is not the same thing, or two different things. And I want to explain you what's the difference. So, first of all, what is actually a key? So a key is a unique identifier, okay, there's a typo there, for a row in a table. That means everything that uniquely identifies a row in a table is a key. There are different types of keys, but we will come to this. Every key has the following properties. So a key is always unique within the table, because otherwise it couldn't uniquely identify a row. It can be composed or standalone. So a standalone key would be just an ID. A composed key would be like a natural key, for instance, first name and last name. Okay, this can have some conflicts, but in a very small environment where you have just one class in a database with 30 entries, it's very unlikely that you have two people with the same name. So you could go for first name, last name, or first name, last name, birth date. It's even better. This could be a natural key. If it is uniquely identifying every row in your table, it is a key. A key can be natural or surrogate. That's basically the same what I said before. So a natural key is something not artificial, so it's natural, like first name, last name, columns that are actually from the object and not just created for the database. And a surrogate key would be an ID, for instance, that just counts up for every new row, like an identity column. So this is the definition of a key. And best practices for keys are that the primary key should be as narrow as possible. This is due to the tree size. You learned about root nodes, intermediate nodes, and leaf nodes. So the leaf node is always the same size because we have all the data from the rows in there. But in the root and the intermediate node, we have only the columns or the key columns or the key column. And if we have more than one column there, and then the problem is that we may need more intermediate nodes, and hence may add another level on the Btree, making one unnecessary I/O operation more than we actually could do when we would have chosen a more narrow key. So because of those settings, it's best to take int or 8-bit int to big int with an increasing identity column, which basically best practice. And also what is really a benefit is if the key never changes, so if the key can never change. So an ID is perfect for this because it is just increasing and never changing. For natural keys, you have to be careful. For instance, if you have a table where the last name is involved, the last name may change at some point if somebody gets married. And then you have the problem that the row will have to be reallocated throughout the whole order, because if the primary key is on last name, first name, then all Millers will be ordered in a certain all entries will be ordered, and the Millers are probably in the middle somewhere. If now a Miller marries and gets the name something with A, for instance, then it, of course, due due to the order of the table, it needs to be put to the front of the table, so it needs to be reallocated throughout the index, which is an expensive operation and should not happen so often. All other keys that are not the primary key are called secondary keys or alternative keys. For instance, a business key, if you have to handle data at your work, or what you often heard, maybe the name business keys, which is nothing more than a natural key used in business, but it's also a key. It needs to be unique throughout the table. And just one slight remark: a foreign key is not a key on the table. It refers to a key. So it is a key, but not on the table where it is a foreign key. There it's just a reference to a key on another table, of course. And here is some example for keys in SQL Server. So primary key are identified by primary key constraint. And only one primary key is allowed per table, the same as for clustered indexes, but still they are not the same. A key is a logical construct. A key is nothing about implementation of a table, and a clustered index is a physical construct. So alternative and secondary keys you can identify by creating unique constraints on your table, like you see in this example. One remark: when you don't do anything strange or irregular, if you do a create table statement like this, the primary key will always also be treated as a clustered index. So this is where the confusion comes from. The primary key always, if you don't specify otherwise, will be also a clustered index. Since both can only happen once on the table, it makes sense to combine it. But you can also have non-clustered primary keys that are built on non-clustered indexes. It is possible. It is not very usual, but it is possible. And one last remark for keys and indexes here: the primary key is a clustered unique index that is not nullable. This is the default setting. And a unique index is a non-clustered unique index. You can also create non-clustered indexes that are non-unique. Yeah, and that's basically all. Keys are logical and implemented through indexes that are the physical counterpart for it. So now we talked a lot about indexes and stuff, and this thing with the index seek is really crucial to understand. I think maybe next time we can revisit heaps a little bit and talk about heaps, how are indexes behaving on heaps. Or maybe we do some sessions on how the order on a clustered index is actually affecting performance. It would be also interesting. One of those follow-up things I will do in a few weeks, or maybe next week even, which seems to be interesting. Therefore, I will also tinker a little bit on the software I showed you before. So if you have questions, then come up with them in the comment area, and I will be happy to answer them. Maybe I can also take them to a new video to explain some stuff raised in the questions. So thank you for tuning in, and have a nice evening. See you next time. Bye.